Hello, everyone. My name is William K. Moses Jr., and today I'll be talking about the awake complexity of distributed minimum spanning tree. This is joint work with John Augustine and Gopal Pandurangan. So, what's going to happen in this talk? First, I'm going to explain the problem solved and the model taken into consideration. And once you understand that, I can then explain to you why you should even care. Why stick around for the rest of this talk? And then hopefully, once I've convinced you that it's worth sticking around, I want to look at a few interesting ideas. One is the lower bound, the product lower bound in particular, and the other is how we're approaching these algorithms. Specifically, we'll look at the randomized algorithm. After all of that, I'll wrap up. So, without further ado, let's look at the problem. What are we trying to do in this paper? Well, in this paper, we're trying to construct a minimum spanning tree, an MST, of some input graph. And the model we consider is the congest model. And finally, what are we trying to optimize when we find solutions? We're trying to optimize something called awake efficiency, or sometimes also called energy complexity. Now, let's look at each of these terms in turn. First, what is a minimum spanning tree? Well, you have some graph, each edge has some weight attached to it, and you want to find a spanning tree. So these red edges, for instance, that spans all the nodes. And the extra constraint put on it is that the sum of the weights of the spanning tree, of the edges chosen, should be the minimum of all possible spanning trees for that graph. So minimum spanning tree. All right, this is the problem we're targeting. Let's look at what model we're going to be using. So in this model, it's a distributed computing model where we have n nodes, each with a unique ID, and each node knows the value of n. Furthermore, the nodes are connected in some arbitrary manner, and this is the congest model. What does that mean? Well, time proceeds in rounds, and in each round over a given edge, nodes can send and receive a constant number of messages, each of size log n bits. So there's congestion on the network edges. Now, with the model taken care of, let's look at the metrics by which we measure the quality of solutions. In other words, what is this awake efficiency? So, as mentioned, this is a synchronous setting. So, what does that mean? In each round, a node can either be awake or asleep. For example, in this figure, black nodes are awake and white nodes are asleep. Now, what does that the algorithm designer, he can control when the nodes are asleep and when they're awake. And the nodes know the current round number. So what is the challenge introduced by this? Well, messages can only be exchanged across an edge when both nodes are awake in the same round. In other words, if you consider this edge here, the black node cannot communicate with this white node because this is asleep. Only when both nodes are awake can a message be exchanged. And this is what introduces an issue or a challenge into the game. Because you, as an algorithm designer, must figure out when these nodes should wake up so that you can still minimize the number of rounds they're awake. Speaking of that, what are the actual metrics we're using to measure solutions? In other words, what is this awake efficiency? It is the number of rounds that any node is awake. No, let me be more specific here. Consider a given node, count the total number of rounds it's awake for, and take the maximum value across all nodes. That is the awake time. And the other metric we use to measure algorithms is the usual traditional running time, also known as round complexity. What is that? Essentially, from the start of the algorithm until the end of the algorithm, that is, until the last node has performed some computation, how many rounds have elapsed? That is the round complexity. All right, with the problem defined, let's move on and answer the important question of why should you care? So, Why care about MST? Well, it is a long-studied problem, and it's long-studied in the congest model, approximately 40 years now. And over the course of so many years, it's pretty much been established that d plus square root of n is a tight bound on the amount of time it takes to solve this problem. Well, the runtime of the problem is this value, and this is tied up to log n factors, where d is the diameter of the graph, and n is, of course, the number of nodes in the graph. So then you might ask, look, if these bounds are tight, so what? Isn't it done? Well, you have to ask yourself the question, is it really necessary that all nodes need to be awake that long? And you might ask us, why even think about this? Is there any reason to consider this? And the answer is yes, because other problems have been worked on, and it has been shown that you can actually get awake times that are asymptotically less than run times for problems like, for example, MIS. And that's quite interesting because it's not just slightly asymptotically less, sometimes it can be exponentially less. And that brings us back to MST. If this is a question that's being looked at in other problems, what's been done so far for MST? And the answer is not much. Well, let's be a little clear about this. Spanning tree has been looked at, and in fact, an O of log n, a wake time solution, was proposed by Barenboim and Maimon in DISC 2021. But the issue is that technique cannot be extended to MST. So then, that is what we're going to look at today. And I just want to also mention the reason we keep saying awake complexity and we also mention energy complexity is because some of the time in, let's say, the congest model, when we talk about this complexity measure, it's called the wake complexity. And in the radio model, the similar complexity measure has been studied for many years now, and it's called the energy complexity there. But they're pretty much the same. So with that said, what are we trying to do? We're trying to look at MST and trying to find an algorithm that gives an awake complexity that is asymptotically much less than d plus square root of n. How much less? And how much less compared to log n? Well, turns out we also can get an O of log n time algorithm. And it turns out even more than that, that we show here a lower bound that says any randomized algorithm for MST would take log n awake time. But all right, that's the awake time. What about runtime? Thing is, we get a runtime of n log n. And you might say, but wait, wasn't the runtime normally d plus square root of n? Isn't this so much more? To that, I would say, hold on a second, because in this paper, we also show that for any algorithm that's designed to solve MST, the product of awake time and runtime is omega tilde of n. And here tilde hides polylog factors, polylog of n. In other words, the solution we're proposing here is optimal up to log n factors, polylog factors. And it's absolutely optimal with respect, or asymptotically optimal with respect to awake time. But that's not all, because sure, this is a randomized algorithm. Next, you'll ask us, can we remove the randomness? And we say, yes, yes, you can. The only issue is runtime increases slightly. In fact, we can actually reduce the runtime at the slight cost of an extra log star n factor in the wake time. And finally, to complete this picture, we also propose a family of randomized algorithms, our trade-off MST algorithms, which take some value k as input, an integer, and it basically gives you some awake time and a corresponding runtime for that parameter. All right, so this is what we show. Let's actually talk about what you get from this paper, because I'm sorry, what you get from this talk. In this talk, we'll briefly talk about the lower bound technique we use. We'll talk about the technique we're using for a randomized algorithm. And finally, we'll briefly mention this important concept of labeled distance tree. Because not only is it useful in this paper, but it's been useful in other papers. For example, Duflan et al. In PODC 2023, to show that where they used it to get an improved MIS algorithm. Okay, now let's actually look at the lower bounds and the upper bounds. First, the lower bound. This theorem statement might look like a mouthful, but it's roughly the following idea. For large diameter graphs, where diameter is greater than square root of n log n, any randomized algorithm that solves MST with correct probability 1 minus epsilon for some small fixed epsilon has the following property. If the algorithm takes running time small o of c for large n of c, then the awake time is at least omega tilde of n by c. So here, small o of c runtime, awake complexity n by c. The implication here is, for an instance, if you had a algorithm that took n power 3 by 4 runtime, small of that, then the wake time should be at least omega of n power 1 by 4. Or in other words, if you multiply these two together, you see that the product of the wake time and runtime is omega tilde of n. Now, how does the proof work? Well, what we do is we take the problem of set disjointness from classical communication complexity, and we reduce that problem to distributed set disjointness in the sleeping model. And the idea is, if we can solve distributed set disjointness with a low weight complexity, it would imply that we can break the fundamental lower bound for set disjointness, which of course we cannot, which in other words implies that the awake complexity is not too small. And that's how we get the lower bound on awake complexity. But we're getting it for some problem distributed set disjointness. We still have to complete the picture, which is showing that this lower bound applies to MST. And if you can reduce DST to MST, well, then the lower bound also applies. And we do this via an intermediate problem called connected spanning subgraph. And I just want to briefly touch upon point 1 and 2 about how we're actually showing this nice lower bound for energy awake complexity. So in this picture, suppose you have C columns. The idea is, if you have an algorithm that takes small o of C, then it cannot just fully use this path to send information from Alice, say, to Bob. It has to also funnel information through these extra nodes at the bottom, which are some log n nodes. And the idea is, because it funnels the messages through this this tree of nodes, the congestion will be high. And because congestion is high, that implies the awake complexity is high. Because remember, in order to send a message, both nodes need to be awake. And as a result, we get our lower bound on awake complexity. So next, let's look at the randomized algorithm. So what we do is we just use a variant of GHS modified to minimize awake complexity. And what is GHS? Well, each node starts as a cluster. You identify minimum outgoing edges. That is, from this cluster, the smallest edge with the smallest weight. It's called that the MOE. And then you merge clusters across MOEs. And then you repeat this for log n phases, and you end up with all of the nodes forming a spanning tree within one cluster. In fact, not just spanning tree, the minimum spanning tree. And because you can show that in each phase, a constant fraction of clusters merge, totally there'll be log n phases. That's the typical GHS. But then how do we minimize awake complexity? Well, we do that through a few observations. First, for a given cluster in a phase, not all nodes need to be awake all the time. In fact, you just need to pass information back and forth from the center of the cluster outwards and back in, so that you can perform some central computations and you can communicate with adjacent clusters. And in particular, if you set up each cluster so that it is something called a labeled distance tree, you can pair it with transmission schedules, which are just a sequence of 2n plus 1 rounds, such that certain nodes are supposed to stay awake in certain rounds and can communicate if they want. And what is a labeled distance tree? Well, true to its name, it is basically a tree centered at some root node, and the labels are given to each node depending on their distance from this root. So things one hop away are labeled 1, things 2 hop away are labeled 2, things 3 hop away are labeled 3. The idea is, in each phase, you can merge these LDTs together, so until only one LDT is left. And so what does that It requires the LDTs to find the minimum outgoing edge and then merge along them. And we develop procedures so that they can merge peacefully. Great. But there's still a problem. What's the problem? Well, suppose we want an O of 1 awake time per node per phase. What we need is we need each of these clusters to only be really active for a constant number of times per phase. But if you have a long line of nodes that need to merge together, when you actually perform the merges, they can only be done sequentially. So when you have a long line that's larger than a constant, they might have to be awake more number of times, and that's bad. How do we deal with this? Well, we break up the lines. And in particular, what we say is we give a label of heads or tails to each LDT by having them flip coins. And the idea is an MOE is only a valid MOE if it goes from a tails to a heads LDT. Now, you might think, okay, great, we're done. But there's still one other issue, which is, will it still take log n phases? Because remember, you need a constant fraction of the clusters to merge together in every phase. And the thing is, we can show that through the analysis. So we're still set. So we can still use this kind of modified GHS way. And so we have totally log n phases. And in each phase, the nodes are awake only for a constant number of rounds. And the total runtime per phase is O of n. As a result, the MST is constructed with high probability in log n awake time and n log n round complexity. Now, in this talk, we looked at the product of a lower bound and randomized algorithm to find MST. We looked at the product of lower bound. We looked at the product lower bound of awake time and runtime to find MST. And we also looked at the ideas for a randomized algorithm to find MST. But in the paper, you can find deterministic algorithm, the trade-off family of algorithms, and the unconditional awake time lower bound. In terms of future work, one could look at the awake complexity of other problems, and also, of course, look at the awake complexity of problems in other settings, like, for example, when faults are there or the graph is dynamic. And so with that, I'd like to say thank you for your attention and farewell.